Hey, so in this video, we are going to be working with these operators and showing how to calculate some things like expectation values and uncertainty. Um, and so this is actually a problem from Griffiths' book in quantum mechanics. So I'll have the link to the page for this book. Because it's a really nice book. It comes at quantum mechanics very different way than I'm trying to go at it. Um, maybe geared more towards more advanced physics and math students. Um, and but this problem is a great one, and so I will be solving it, and it shows really well how to work with these operators. These are just some equations that we've had in the past, mostly from section 2 that we've dealt with, right? This is the generalized uncertainty principle. Sigma a squared, sigma b squared, right, is for two quantities a and b, is greater than or equal to 1 over 2i times the expectation value of this commutator, and then all of that squared. Q, the expectation value of the observable q, is psi inner product with q hat psi, right, which this is in the integral definition. Then this is the definition of the standard deviation, right? And notice, similarly, uh, the expectation value of q squared will be psi inner product with q hat squared psi, right? Where q hat squared is equal to q hat acting on q hat, right? You act one and then the other. Okay, so now we're going to work with the actual operators that we came up with in this last video, mainly x hat being multiplying by x, and p hat being multiplied, p hat being minus I h bar d by dx. Okay. The first thing is this is not part of the problem. This is just the first thing that I want to do to just start with getting us the actual uncertainty principle, right? We need to get, let's say, sigma x squared sigma p squared. This is, right, 1 over 2i. So the expectation value of the commutator of x hat and p hat squared. Right? Well, now we have to figure out what the commutator of x hat and p hat are. Right? Where this is a commutator of x and minus I h bar d by dx. Right? And how we do this is we use what is called a test function. So what we're going to look at is because this commutator is going to be an operator, right? So the operator, and these operators don't really make sense on their own as long as they're, right, they've got to be acting on a function. So to calculate this commutator, what we'll do is we'll write, so we're looking for the commutator of x and I minus I h bar d by dx times some function f, right? And this is, just by the definition of a commutator, x times negative I h bar d by dx, right? Minus negative I h bar d by dx, right? And so this is, times x acting on f, right? But this f is over here. So if we expand this out a little bit more, and I'm also going to simplify, right, and bring out constants, because constants do commute. So minus I h bar x. Actually, you can take out a factor here of I h bar, as long as then you just make this, plus plus. So this is equal to I h bar times, we have x df by dx, right? Take that in, right? Minus or sorry, this is negative, right? Plus, we then have I h bar. Oh, sorry, we took out the I h bar. So this is d by dx of x times f, right? We're taking the derivative of that whole thing. And now, this is where things start getting different, because when we're doing this, we have to use the product rule, right? So this is I h bar times, so negative x df by dx, right? Plus, so first times the derivative of the second, so x df by dx, right? Plus the second, f, times the derivative of the first. The derivative of x is just 1, right? So f times 1, right? And this is equal to, right? This cancels, and this is I h bar f, right? So order does matter, right? If you multiply by x and then take the derivative versus take the derivative then multiply by x, they are not the same thing, right? And in fact, if we now get rid of the f's, we use the f, it's the test function. That's how we calculate the commutator. Now we remove this f, again, just to write it in a more compact notation. This commutator is equal to I h bar, right? The commutator of x and p is I h bar. So, then we also know that the expectation value, right, of this, I'm going to just erase some of the equal signs so I can write this well. The expectation value of that is the expectation value of this, which is the expectation value of I h bar. It's a constant, so the expectation value of a constant, right, if you measure it a bunch of times, it's going to be the same thing, right, I h bar, right? And so, putting this into the uncertainty principle, we get that sigma a, or not sigma a, sigma p, or sigma x squared, sigma p squared, is greater than or equal to 1 over 2I times I h bar, right, squared. So, if we, these i's are going to cancel, and then we square the whole thing, and I'm going to write in blue our uncertainty relation. Sorry, we square root the whole thing. Sigma x, sigma p is greater than or equal to h bar over 2 quantity squared, which is, we take the square root. So it's greater than or equal to h bar over 2. And this is the uncertainty principle we all know and love, and we derive that from the x and p operators, as well as this general uncertainty principle that we derived back in section 2. So in fact, I'm going to move this. I'm going to put it up here so I have a little bit more space to work. So we know that sigma x, sigma p is greater than or equal to h bar over 2. Okay. So now to the problem from Griffiths that will use all of this information and give us some practice normalizing a wave function. And I'm not going to do all the calculations on here. I'm going to all these calculations have already been done. I'm going to write the equation, and then instead of making going through the whole process of calculating everything, I'm just going to go ahead with the answer. So the first thing is I've got some wave function. Psi of x is this piecewise function. It is a times little a squared, so capital A times little a squared minus x squared when negative a is less than or equal to x is less than or equal to a. So that's x is in between negative a, and 0 otherwise. So the first thing is we have to find the constant a to normalize this wave function. And so what we'll have to do is we have to use our normalization condition that we know the integral from negative infinity to infinity of psi squared, psi norm squared, but it's real, so right, dx is equal to 1. Sorry, 1. Right, and if we write this out, this will be, right, that's the integral from negative infinity to infinity of, well, actually, first thing that we can do is, and I think I may have mentioned this in our video on improper integrals. If I've got a function, if I graph this function, it will look something like this. So quadratic, and it hits at a and negative a, and 0 everywhere else, right? And so if I want this area, right, what I'm looking for is this area, right? This is the integral of the function from negative infinity to infinity, the total area, but it's also the integral from negative a to a, right? I can actually simplify this and the bounds just because the wave function is 0. If the wave function is 0 and then, like, from certain points, we don't have to integrate over that, we're just going to get 0. Right? The area from negative infinity to negative a, all this area is 0, and all this area is 0, so the only area we're counting is in here. Right? So that's our first simplification. So this is the integral from negative a to a, and that's an important step to know. And then this is a norm squared times a squared minus x squared, norm squared, but it's real, so just squared, dx, right? And a squared is a constant, right? So you can take that out. This is a squared, yeah, the absolute value of a squared, times this integral, and this is one of the calculations. This has already been done for us. Okay, so this integral is equal to 16, a squared times 16 little a to the 5th over 15, right? And we know that this is equal to 1, right? And so one possible answer for a, again, this is a magnitude squared, so this could actually be any phase, like an e to the I theta, right? This could be any phase, times, right? But I'll just write the easiest answer. The square root of 15 over 4a to the 5/2 power, right? If you just take the square root of this, you divide the divide the exponent by 2, right? And then you could also, this could be times I, or times, e to the 3i, or whatever, right? As long as it's a phase. But we'll just stick with the easy one because no need to make it more complicated. So this is the first part, right? We've figured out the a, and I'm just going to write all the information that we have. We know that a equals the square root of 15, right? This is how we normalize the wave function. Square root of 15 over 4 little a to the 5/2. Okay. I'm going to erase this now. We'll move to the next part, which is they want us to find the expectation values of, or I'll go tell you what the problem is in general, and then we'll find out all these values. So they want us to find the expectation value of x. They want us to find the expectation value of x squared, expectation value of momentum, expectation value of momentum squared. And then, given all this, well, why don't we just go and find the standard deviation of position and the standard deviation of momentum, right? So we find all of this, and then we can check to see if this wave function violates the uncertainty principle, right? And if it violates the uncertainty principle is wrong, right? Because this is a wave function, right? So our theory, right, is that no wave function, no function at all that's normalized can violate this uncertainty principle, right? That it just cannot happen. And so we've got to actually show that. And so we'll test that out with this operator. As a spoiler, or not this operator, this wave function. As a spoiler, the function does observe the uncertainty principle. Otherwise, the uncertainty principle would be wrong, and it is not wrong. So, and I'm going to leave up the graph of this because it will actually have some interesting consequences from A to negative A. Okay. So, first thing we want is the expectation value of position, right? Well, that's just if we, use our this equation. This is the integral. Now, it's the integral over all possible values of x, right? But the possible values of x are between negative a and a. So all of our integrals are going to be between negative a and a, right? Because we have these wave functions there. And the wave functions are going to be 0, so the area is going to be 0 except for between negative a and a. Again, hopefully that geometric argument that makes sense. So this is psi star, but again, we don't have to do anything, special for that because it's this is a real wave function. So it would be a times 8 squared minus x squared times x times a squared minus x squared dx. And it turns out that this integral is equal to 0, right? If you do this integral. There's actually a trick to doing it, but I'm not going to get into that right now. All you need to know is this integral is 0, which makes sense because the particle is equally likely to be left of 0 as it is to be right of 0. So its average value should be 0, right? Now, its average position squared is not necessarily 0. In fact, it couldn't be 0. Right? The reason this average is 0 because this is what are negative positions, these are positive positions, so they average out. But these are still positive position squares, right? Because the negative goes away. Right? So I'm going to rewrite that. I didn't mean to erase that part. Okay. So now let's find the expectation value of momentum. Oh wait, no, sorry. We're still doing x squared. So x squared, value of x squared is from the integral from negative a to a, right? X squared hat will be just x squared, right? Because it's x and then another x. Okay, so using that, this is a times a squared minus x squared. X squared. Oh, and I think I forgot the a, but it doesn't matter because the integral will still be 0 on the last one. But this one, the a's will actually matter because the integral is not just 0. A times a squared minus x squared dx. Okay, and if you do the integral and use our value of a that keeps this thing normalized, you will find that this is equal to a squared over 7. Some weird numbers that you get in here, but they all will end up working well with the uncertainty principle. So that's all we care about. Okay. So again, I'm just showing you the integral that you would do, and then I already know the results of all of these integrals. Okay, let's look at how do we do the expectation value of momentum. Well, that will be the integral. Again, we're integrating from negative a to a, because we're integrating over x, of a times a squared minus x squared times negative I h bar d by dx of the wave function a squared minus x squared, right? So the derivative of that dx. Okay, and if you do this integral, hopefully this integral makes sense as times minus. So you could bring the minus out front, but I just wanted to show you the whole work. If you do that, the expectation value of momentum, this integral is also going to be 0. So this is equals 0. Okay. Next, we're almost done with this problem. Again, this problem will take a lot more work if you actually have to go and do these integrals. So that's why I'm not, as long as you get the point in how to calculate these quantities, that's what the important part is. Expectation value of p squared will be, well, p hat squared, right, is minus I h bar d by dx acting on minus I h bar d by dx. And if you remember, the derivative of the derivative is the second derivative. Negative I h bar times negative I h bar. Negative I times negative I is negative 1. So this is negative h bar squared d squared by dx squared. And note, for the last integral, you would have had to actually take the derivative of the function before you did the integral. So it wouldn't, or use integration by parts, but I would definitely not recommend doing that, because then you'll still have an integral and it'll turn out ugly. So you just take the derivative and then do the integral, do the bounds. So this is going to be the integral from negative a to a of a squared minus x squared. Right, and again, these are using the value of a that we found, root 15 over 4a to the 5 halves. Times negative h bar squared. Let's d squared by dx squared. Right, the second derivative of a squared minus x squared, then that dx. So you take the derivative, then take the derivative again, you plug in these values for a, you do the integral, and in the end, you will get 5 h bar squared over 2a squared. So if I write that here, this is 5 h bar squared over 2a squared. Okay, so now we are on our last few parts. I'm going to erase the wave function now. Just we're done really using that, because now all we need to use is this equation up here and our values for the expectation values. Note, the expectation values of x and p are not always going to be 0. It just turns out in this problem they are. So we know sigma x is the square root of the expectation value of x squared minus the expectation value of x squared, right? Which is, expectation value of x squared is a squared over 7. So this is the square root of a squared over 7 minus 0. Right? And so this will be a over the square root of 7. Okay, so I'll write that one down. So this is equal to a over the square root of 7. Right, and that makes sense. The wider the possible positions are, right, the wider that parabola is, wider the parabola is, the more deviation in the position there's going to be, right? Because that would make sense. The positions, the probability distribution of the positions is more spread out. Okay, now we've got use sigma p is the square root of expectation value of p squared minus expectation value of p squared. This is the square root of 5 h bar squared over 2a squared minus 0. So this is the square root of 5 over 2 times h bar over a. So this is equal to the square root of 5 over 2 times h bar over a. And now finally, we see that sigma x, sigma p is, using these values, this is a over root 7 times root 5 over 2 h bar over a. The a's are going to cancel. And then we can combine, so root 5 over 2 times 1 over root 7 is going to be root 5 over 14 times h bar. Now, you may not know off the top of your head what the square root of 5 over 14 is, but thankfully I already know what that is, which is, this is actually approximately, it's not exact, it's an irrational number, this is approximately 0.598 h bar. And is 0.598 h bar, is that greater than or equal to h bar over 2, which is 0.5 h bar? Right, because it is. It is indeed. Right, because 0.5 is less than 0.598. So the uncertainty principle actually works in this case, as it should, because it should work in any case. But we have now shown with an actual wave function, using our operators, that the uncertainty principle holds, and we've also calculated all this stuff. So hopefully you now understand how to calculate things using these operators, and that is just the tip of the iceberg on how useful these operators are. In the next 2 videos, we will be laying the solid foundations, and in 2 videos, we will finally arrive at the Schrödinger equation, the central equation to quantum mechanics. And I will see you in the next video.